Namaste, future tech leaders. Cello, let's begin. Today, we're going on a little adventure, following a single bit of data, just one bit, to understand the building blocks of all the digital magic that surrounds us.
You know, it all comes down to something pretty simple: memory and logic, just working together over time. So let's demystify this, right? We're going to break down how digital systems store, move, and count information. And believe me, these three fundamental operations, they're what make everything work, from your phone right up to a massive supercomputer.
Okay, so first things first. Our little bit of data, it needs a place to live, right? It can't just be floating around in the circuit aimlessly. And that home, well, we call it a register. So let's take a closer look and see what this home is actually made of.
Okay, so at the very heart, the absolute core of every single register is this tiny fundamental switch. It's called a flip-flop. Now, the best way to think of it is like a one-bit locker. It is literally the simplest memory element that exists, and it can only hold one single piece of information, either a 1 or a 0. That's it, nothing more.
But you might be asking, what if you need to store more than just one bit? I mean, what about the number 4, which is 100 in binary? Well, it's actually super simple. You just line up the flip-flops. An n-bit register is just a cascade of n flip-flops. So a 4-bit register, that's just 4 of these lockers side by side, all ready to hold a 4-bit word. It's like having a row of dabbas for your data. Simple, nah?
So what's its job? It's really, really simple. Its fundamental job is to store binary data, period. You can think of it as static memory, just a primary holding place for information before it gets processed. Okay, so storing data is great. It's essential, but let's be honest, it's not very useful if we can't move it around, right? And that's exactly where our next component, the shift register, comes into play. You'll see how it builds directly on this idea of storage. I want you to picture a conveyor belt at a factory. You know, you see an item and it moves one spot forward with every pulse of the machine. Well, a shift register does exactly that, but for our bits. With every single clock pulse, and you can think of that as the regular heartbeat of the circuit, the entire line of bits we've stored, it just shifts over by one position. So cool. And just like those conveyor belts, you can load and unload them in different ways. Well, shift registers come in 4 main flavors, and it's all based on how data goes in and how it comes out. You can do it serially, that's 1 bit at a time, or in parallel, which is all the bits at once. Now, what's really powerful here, and this is what I want you to see, is their ability to convert data between these two forms, serial and parallel. And that is absolutely critical for getting different parts of a system, parts that talk at different speeds, to communicate with each other. So let's nail this down. If a register is a locker, what's a shift register's job? Its main job is both storage and transfer. See, a regular register is static, it just holds things. But a shift register, it's dynamic. It doesn't just hold information, it actively moves it. All right, so let's recap where we are. We can store data and we can move it around. Awesome. But how do we keep track of things? You know, like how many times a button has been pressed, or even just how many clock cycles have gone by. For that job, we need a counter. A counter is, well, it's just like one of those hand clickers, you know, the ones they use to count people entering a stadium. Every clock pulse is like a click. And with each click, the counter's state just updates to the next number in its sequence. It just goes 0, then 1, then 2, and so on with every single tick of the clock. And don't let their simplicity fool you. These devices are literally everywhere, and they are absolutely critical. They work as timers, they record events, and they control the sequence of operations in much more complex circuits. In fact, one of the most important parts of your computer's CPU is something called the program counter. And guess what? It's its job to tell the processor which instruction to run next. That's how important these are. Okay, now it's important to note that not all counters are created equal. The main difference really comes down to timing. And this is a very important funda to get clear in your head. We have 2 main types: asynchronous counters, which we often call ripple counters, and then we have synchronous counters. And this slide, well, it illustrates the difference perfectly. Look, in a ripple counter, only the very first flip-flop is connected to the main clock. Its output then becomes the clock for the next flip-flop, and so on, creating this ripple effect, just like a line of falling dominoes. It's simple, for sure, but it's also slow. And that's because of something called propagation delay, that tiny, tiny lag as the signal travels from one domino to the next.
Now, a synchronous counter is totally different. It connects every single flip-flop to the same clock. So what happens? They all change together, perfectly in sync, almost like a synchronized dance troupe. This is much, much faster, but yeah, it does require some more complex wiring.
So, what's the key difference? The bottom line? It's all about how they listen to the clock. In a ripple counter, remember, only the first flip-flop gets that external clock signal. But in a synchronous counter, all of the flip-flops get that same clock signal at the exact same time. That's the whole game.
Okay, so let's put it all together. We have registers to store information, we have shift registers to move it, and we have counters to count things. But how do we combine all these pieces to create some intelligent behavior, like a traffic light controller or a vending machine? Well, for that, we need a brain for the whole operation.
And that brain is a design concept we call a finite state machine, or FSM for short. I love this analogy. Think of the registers and counters we've been talking about as the muscles of the system. Well, the FSM, that's the brain that coordinates them all. It's the boss. It tells them when to store, when to shift, and when to count, and it makes those decisions based on inputs from the outside world and its own current state.
Now, designing one of these brains, it isn't magic, not at all. It's actually a very clear engineering recipe. You always start with the specification, which is just clearly describing what you need the circuit to do. From there, you move to formulation, and this is where you create a state diagram. Think of it like a flowchart for the circuit's behavior. Then, after you assign unique binary codes to each state, you get down to the math and derive the actual logic equations. And these equations are what will tell the flip-flops when to change, and that's what ultimately brings your whole design to life.
So let's just quickly recap this whole journey we followed, shall we? It all starts with a single bit finding a home in a flip-flop. We store it. Then it gets moved around by a shift register. That's the shift. We track events using a counter, count, and the whole thing is controlled by a finite state machine, control. Store, shift, count, control. That right there is the fundamental journey of data inside every single digital device you use.
And please remember this. Mastering these building blocks, this isn't just about passing an exam. This is the alphabet of digital design. Seriously, what you're learning right now about registers, counters, and state machines, these are the fundamental skills that are going to empower you to create the intelligent systems of tomorrow. I'm talking about new AI hardware, tiny little IoT devices, the next generation of super fast computers, all of it. So please stay curious, keep building, and never ever stop learning.